Hello. In this example, we'll calculate the plastic moment of an I-shaped beam section that is built up by welding 8" by 1" flanges to a 20" by ½ web. All material in this section has a yield stress of 50 ksi. The first step in this process is to locate the plastic neutral axis, and then the second step is to calculate the plastic moment itself. We'll conclude by discussing the plastic section modulus for the cross-section and different options that are available for different types of cross-sections. This example builds off an earlier example problem where we examined the elastic bending properties of this cross-section. In that example, we calculated the moment of inertia, the normal stresses in the cross-section resulting from a bending moment of 600 kip-feet, and then the bending moment that will cause first yielding in the cross-section. If you haven't worked through that example yet, then you can watch it using the link shown on this slide. In general, the plastic neutral axis of a cross-section can always be found as a location where the sum of the plastic force resultants above the plastic neutral axis is equal to the sum of the plastic force resultants below the plastic neutral axis. We can illustrate that process here, where we'll sketch a short length of the beam in elevation next to the sketch of the cross-section. If we assume that a positive bending moment is applied, it looks like a double-headed vector acting on the cross-section with the heads of the vector pointing to the left, which, per the right-hand rule, indicate that compression is acting at the top of the section. The same bending moment can be illustrated by using a pair of curly moment vectors applied to the length of the beam shown in elevation, which again indicate that the compression is acting at the top of the section. With that, and assuming that all of the elements are loaded to their yield stress, the distribution of stresses on the section would look like this. This is referred to as a plastic stress distribution. Finally, the force resultant at the top flange is equal to the yield stress of the steel acting over the area of the top flange, and the force resultant in the part of the web above the plastic neutral axis is equal to the yield stress of the steel acting over the area of the web above the plastic neutral axis. The force resultant in the part of the web below the plastic neutral axis is equal to the yield stress of the steel acting over the area of the web below the plastic neutral axis. And finally, the force resultant in the bottom flange is equal to the yield stress of the steel acting over the area of the bottom flange. If we have selected a correct location for the plastic neutral axis, then the sum of the force resultants above the plastic neutral axis will be equal to the sum of the force resultants below the plastic neutral axis, at least for the case of a beam with no axial force. In this case, where we assume that the plastic neutral axis is in the web, that can be written as the force resultant in the top flange plus the force resultant in the web above the plastic neutral axis is equal to the force resultant in the web below the plastic neutral axis plus the force resultant in the bottom flange. That equation is written again here on this slide. P sub Ft plus P sub Wa is equal to P sub Wb plus P sub Fb, where again the assumption is that the plastic neutral axis is in the web of the cross-section. However, this case is a bit more straightforward. Since this is a doubly symmetric section, and since the section is homogeneous, meaning that all of the elements of the cross-section are made of material with the same yield strength, we can tell by observation that the plastic neutral axis will be at mid-height of the section. We can select the top of the cross-section as a point of reference and then use the notation y bar sub p to denote the location of the plastic neutral axis relative to the top of the steel section. However, it is sometimes more convenient to reference the location of the plastic neutral axis relative to the top of the web rather than relative to the extreme fiber of the cross-section, since this makes our calculation simpler in some cases. Thus, we will use the notation y bar sub pw to denote the location of the plastic neutral axis measured from the top of the web when it is convenient. Going back to our sketch of the stresses and force resultants on the cross-section, we can add that dimension, y bar sub pw, here at the left to identify the location of the plastic neutral axis more specifically. If we move things around a little bit to give ourselves more space to work, we can calculate the force resultant in the top flange as 50 ksi times a flange width of 8" times a flange thickness of 1", which is equal to 400 kips. Next, we can calculate the force resultant in the web above the plastic neutral axis as 50 ksi times the depth of the web above the plastic neutral axis, 10 inches in this case, times the web thickness of a half an inch, which is 250 kips. Next, we can calculate the force resultant in the web below the plastic neutral axis as 50 ksi times the depth of the web below the plastic neutral axis, 10 inches again, times the web thickness of a half an inch, which is again equal to 250 kips. And then we can calculate the force resultant in the bottom flange as 50 ksi times the flange width of 8 inches times the thickness of 1 inch, which is again equal to 400 kips. Finally, we can confirm that the sum of the forces above the plastic neutral axis and the sum of the forces below the plastic neutral axis are equal. Both are equal to 650 kips, which indicates that the plastic neutral axis is in fact located 10 inches below the top of the web or 11 inches below the top of the cross-section. After the location of the plastic neutral axis has been determined, the magnitude of the plastic moment can be calculated. The plastic moment of a cross-section can always be found by summing the moments that the force resultants of a fully plastic section create about some point. We often choose to sum those moments about the plastic neutral axis of the cross-section. In this equation, m sub p is the plastic moment, and p sub I is a plastic force resultant of each element in the cross-section. We often choose to sum the moments about the plastic neutral axis itself. When that is the case, d sub I is a distance measured from each of the plastic force resultants to the plastic neutral axis. We'll return to our sketch of the stresses and force resultants on the cross-section and calculate the plastic moment for this cross-section. Next, we'll label each of the plastic force resultants explicitly. Then we can observe that the force resultant in the top flange is 10.5 inches above the plastic neutral axis. Thus, we can calculate that the moment created by that force resultant is 400 kips times the distance of 10.5 inches, or 4,200 kip inches. Next, we can observe that the force resultant in the web above the plastic neutral axis is 5 inches above the plastic neutral axis. Thus, we can calculate that the moment created by that force resultant is 250 kips times the distance of 5 inches, or 1,250 kip inches. Next, we can calculate that the moment created by the plastic force resultant in the web below the plastic neutral axis is also 1,250 kip inches. And finally, we can calculate that the moment created by the plastic force resultant in the bottom flange, which, like the top flange, is also equal to 4,200 kip inches. Note that even though 2 of the plastic force resultants are acting to the left and 2 are acting to the right, that they all act to create a counterclockwise moment about the plastic neutral axis. Thus, they are all treated as positive. The next step is to take the summation of these moments that each of these resultants create about the plastic neutral axis, and we find that the plastic moment is equal to 10,900 kip inches, or 908 kip feet. As a final step, we can calculate the plastic section modulus Z by dividing the plastic moment by the yield stress. For this section, we find that the plastic section modulus is equal to 10,900 kip inches divided by 50 ksi, or 218 inches cubed. Note that this only makes sense to calculate the plastic section modulus for a homogeneous section where the yield stress is constant throughout the section. It doesn't make much sense to calculate the plastic section modulus for hybrid sections since there are at least 2 different values of f sub y in those sections, and it wouldn't be obvious which of the values should be used in the calculations. For homogeneous sections, we have the option of finding the plastic neutral axis and determining the plastic section modulus by working directly with the areas of the elements in the cross-section instead of working with the plastic force resultants of the elements of the cross-section. Before we get into the details, we should formally define what a homogeneous section is. A homogeneous section is a section where all of the elements are made of the same grade of steel. Specifically, all the elements have the same yield stress F sub y. In contrast, a hybrid section is a section where the different elements of the cross-section are made of different grades of steel. For an I-shaped section, typically one or both flanges will have a higher yield stress than the web. Finally, to be complete, a composite section in this context is a section that includes both steel and concrete. For a beam section, this usually means that there is a concrete slab on top of the steel section. Importantly, there has to be a shear transfer mechanism between the steel and the concrete, however, for the two materials to work together as a single cross-section. If we return to the problem definition, we again see the statement that all steel has a yield stress of F sub y equals 50 ksi, which means that this is a homogeneous section. So once again, for the case where the plastic neutral axis is in the web of the cross-section, this equation holds, where the plastic force in the top flange plus the plastic force in the web above the plastic neutral axis is equal to the plastic force in the web below the plastic neutral axis plus the plastic force in the bottom flange. This equation always holds for homogeneous sections or hybrid sections, as long as the section is I-shaped and as long as the plastic neutral axis is in the web. We can rewrite this equation by factoring out the yield stresses of the elements of the cross-section, where each of the areas is defined as shown here. And for the case of a homogeneous cross-section, where the yield stress of the material is constant, the value of F sub y cancels out entirely, and we can say that the plastic neutral axis is located where the area above the axis is equal to the area below it. This concept is sometimes referred to as the equal area axis theorem, and the equation shown in this slide holds for I-shaped homogeneous sections where the plastic neutral axis is in the web. While the plastic moment of any cross-section can be found by summing the moments that the force resultants of a fully plastic section create about some point, usually the plastic neutral axis, the plastic section modulus of a homogeneous section can be found directly by summing the moments that each of the areas of the elements in the cross-section create about some point, usually the plastic neutral axis. We can prove this mathematically, starting with the plastic moment as a summation of the moments created by the plastic force resultants about the plastic neutral axis. If we substitute F sub y times A for P in this equation, then if F sub y is constant for all the elements in the cross-section, it will come out of the summation. Dividing both sides of this equation by F sub y yields Z on the left-hand side, and the summation of A sub I times D sub I on the right-hand side. If we apply this to our current example, we can calculate the moments that each of the areas of the elements of the cross-section create about the plastic neutral axis. Taking the summation of these moments, we find that the plastic section modulus, Z, is 218 inches cubed. This is Z sub x, since this is the plastic section modulus for bending about the x-axis of the cross-section. Finally, we can calculate the plastic moment by multiplying the plastic section modulus by the yield stress of the section. M sub P is equal to 50 ksi times 218 inches cubed, which is equal to 10,900 kip inches, or 908.3 kip feet. Another trick that we can sometimes use is to compare our calculated section properties to section properties that are published for similarly proportioned rolled shapes. A W21 by 93, for example, has similar dimensions to the built-up section that we have been working with in this example, and we can see that the published value for the plastic section modulus, Z sub x, is very similar to the value that we calculated. In summary, we calculated the location of the plastic neutral axis and found it to be located 11 inches from the top of the cross-section, or 10 inches from the top of the web. This confirmed what was probably obvious to most, since this was a doubly symmetric homogeneous section where the plastic neutral axis could be determined by observation to be at the geometric center of the cross-section. Then we went on to find the plastic moment of the cross-section to be 908.3 kip feet, and the plastic section modulus to be 218 inches cubed. Since this was a homogeneous cross-section, where all of the cross-sectional elements had the same yield strength, we were able to perform those calculations using two approaches. First, by working with the force resultants on the fully plastic section, and then by working directly with the areas of the cross-sectional elements. Had this been a hybrid cross-section instead of a homogeneous cross-section, then we would not have been able to work directly with the areas of the cross-sectional elements. We would have had no choice but to work with the force resultants on the fully plastic section. So for homogeneous cross-sections like this, which approach is better? Well, it's really up to the engineer to decide. Most of the cross-sections that we work with in the design of building-type structures tend to be rolled shapes, which are inherently homogeneous and are often doubly symmetric. In those cases, it's perfectly acceptable to work with areas of cross-sectional elements. However, in the design of bridges, it's more common to work with cross-sections that are built up by welding plates together. Those cross-sections are more likely to be only singly symmetric and are more likely to be hybrid sections. In those cases, there is no choice but to work with the force resultants of the cross-sectional elements on the fully plastic section. One additional consideration is that when we start to work with composite beam sections, where we have both steel and concrete in the same cross-section, we will also have no choice but to work with the force resultants on the fully plastic section.